All right, let's jump right into it. Welcome to this explainer. I am super excited to have you here today as we decode the abstract world of computer networking. Our mission is pretty straightforward. We're going to take this invisible, highly complex digital highway and break it down into clear, logical building blocks. Whether you're here to solidify your foundational knowledge or you just really want to grasp the absolute magic happening behind your screen right now, you are in the perfect place. So, let's get started.
Have you ever actually stopped to think about how a simple text message travels across the entire globe in just milliseconds? I mean, you hit send, and literally before you've even blinked, a friend on a totally different continent is reading your words. It honestly feels like magic. But as we know, it's actually the result of this incredibly precise, layered system of hardware and protocols. And today, we're going to pull back the curtain and see exactly how that journey happens.
So, here is our roadmap for getting there. 1. The basics of networking. 2. Sizing up network types. 3. Mapping connections. 4. Understanding IP addresses. And 5. The 7-layer OSI model.
Let's start right at the foundation. Section 1. The basics of networking. Look, at its absolute core, the definition of a network is surprisingly simple. It's really just a collection of interconnected computers and devices that communicate and share resources. You don't need a massive humming server farm to have a network. Take a super practical, everyday example from our source material, a printer and a mobile phone. When you link your phone to that printer to print out a PDF, congratulations, you've just formed a functional network. Networking is simply the act of designing, implementing, and managing those kinds of connections.
So, now that we've got the baseline, how do we actually categorize them? Let's move to Section 2, Sizing Up Network Types.
We categorize networks basically by their geographical footprint. And a really cool way to visualize this is using travel time as a proxy for scale. It's exactly why dropping a file to a device sitting next to you feels instant, but a global video call might have that awkward slight delay. If a data packet takes roughly 1 millisecond to travel, you're likely in a PAN, a personal area network. That's your workspace, your laptop talking to your Bluetooth headphones. Step that up to 10 milliseconds, and you're in a LAN, a local area network. Think of your home Wi-Fi or a standard office building. At 100 milliseconds, you're traversing a MAN, a metropolitan area network, connecting multiple buildings across an entire city. And finally, at 1 second or more, you're crossing a WAN, a wide area network. This is the vast telecommunications infrastructure spanning countries and continents. In fact, the internet itself, that is just the ultimate WAN.
All right, knowing the scale is great, but how do we actually arrange the cables and hardware to form these things? That brings us to Section 3, Mapping Connections.
The big concept we need to talk about here is network topology. Topology is essentially the structural blueprint for how these devices interact. It dictates both the physical layout, like where the literal copper or fiber cables are plugged in, and the logical layout, meaning how the data actually flows between the nodes. And by nodes, we just mean devices like switches, routers, computers, you name it.
Now, there are two heavily contrasting blueprints we generally use to build these. In a star setup, every single device is physically connected to a central node, usually a router or a switch. It's highly organized, it's super easy to manage, but, and this is a big but, it has a single point of failure. If that central switch dies, the whole network just goes dark. Contrast that with the mesh setup. In a mesh, the system is totally decentralized. Every device is interconnected with every other device. Yeah, it requires way more cabling and a headache of configuration, but it is incredibly robust. If one path fails, the data simply routes itself around the problem.
Okay, so we've got our hardware mapped out. But for these devices to actually find each other and talk, they need a digital postal system. That's Section 4, Understanding IP addresses.
I want you to burn this number into your memory, 4.3 billion. That is the absolute mathematical limitation of the older 32-bit IPv4 protocol. See, an IP address is just the unique numerical label assigned to every device on a network so data can locate it. But because IPv4 uses a 32-bit structure, it mathematically caps out at roughly 4.3 billion unique addresses. And let's be real, in a world where everyone has a smartphone, a smartwatch, a laptop, and a smart fridge, we blew past 4.3 billion devices a long time ago. The internet desperately needed an upgrade.
And the solution to that bottleneck? IPv6. While IPv4 is that 32-bit purely numeric system stuck at 4.3 billion, IPv6 expands things into a massive 128-bit alphanumeric format. It uses both numbers and letters. The result of that? a capacity of 7.9 times 10 to the 28th power. That is literally enough IP addresses to assign one to every single atom on the surface of the Earth, making the jump from IPv4 to IPv6 completely future-proofs global routing for generations.
Awesome. So we have the physical connections, we have the digital postal system, now we need the universal rulebook that governs exactly how a message goes from a human brain into a physical wire. Section 5, the 7-layer OSI model.
The OSI, or Open Systems Interconnection App model, is kind of like a highly organized multi-story factory that standardizes global communication. Let's break down the top 3 floors first, the user-facing upper layers. We start at the application layer. This is where you actually interact, like your web browser sending an HTTP request. Next, that data moves down to the presentation layer. Think of this as the translator and the security guard combined. It handles data encryption, decryption, compression, and formatting so the receiving system can actually read it. Then it drops to the session layer. This one acts like a bouncer. It handles authentication, verifying exactly who you are when you log in, and it controls the dialogue, making sure the connection stays open as long as you need it to.
Now, before we drop into the lower layers, we have to pause at the transport layer to look at a massive choice the system has to make about how your data travels. It comes down to TCP versus UDP. TCP is connection-oriented. It requires a virtual handshake before sending anything, and it sequences your data, guaranteeing reliable delivery without any errors. It's incredibly safe, but yeah, it's a bit slower. UDP, on the flip side, is connectionless. It just blasts the data out there as fast as humanly possible without even checking to see if it arrived perfectly. So, if you're sending a critical business email, you use TCP. But if you're live streaming a fast-paced video game where speed is way more important than dropping a single frame, you absolutely rely on UDP.
Okay, let's finish our descent into the hardware-facing lower layers of this factory. So, Layer 4, the transport layer, takes that massive chunk of data and chops it into manageable, bite-sized pieces called segments. Then, it passes down to Layer 3, the network layer, which slaps on those logical IP addresses we talked about earlier, both the source and the destination. Next up is Layer 2, the data link layer, which bundles the data into frames and adds the physical hardware addresses. Finally, we hit rock bottom, Layer 1, the physical layer. Here, all of that beautifully structured data is converted into raw ones and zeros, electrical signals or pulses of light, and physically pushed right through the cables or over the Wi-Fi waves.
Actually, I want to quickly zoom back in on that data link layer for just a second, because it introduces a really vital piece of the puzzle, the MAC address. See, while your IP address is logical and can change depending on which coffee shop Wi-Fi you happen to join, your MAC address is completely permanent. It stands for Media Access Control. It's a unique physical identifier hard-coded directly onto the silicon of your device's network interface card by the manufacturer itself. It acts as the absolute final physical destination for any piece of data on a local network.
And that brings us completely full circle. Let's synthesize this whole journey. When you send that text message, it doesn't just magically fly through the ether. First, the data is created by your messaging app. Next, it gets encrypted for security at the presentation layer. Then, it's chopped up into segments for transport. It's mathematically addressed with an IP and physically targeted with a MAC address. Finally, it is transmitted as raw physical bits across cables, through routers, traversing LANs and WANs until it climbs up the exact same 7-layer ladder on your friend's device on the totally opposite side of the world.
So the next time you send off a simple message, just remember the incredible, intricate blueprint working tirelessly behind the scenes to make it happen. But I want to leave you with this provocative thought as we wrap things up today. The 7-layer OSI model perfectly maps how human-operated computers talk today based purely on rules that we engineered. But as we step into this new era where AI networks begin optimizing and even designing their own topologies, will this human-made rulebook survive? Or are we on the brink of an entirely new, incomprehensible blueprint? Some to think about. Thank you so much for joining me on this explainer. Keep questioning, keep learning, and I will catch you in the next one.